Well, welcome back. We're going to continue with the fundamental theorems of calculus, which I started looking at last time, and then we'll move on to finding integrals, both definite and indefinite, which we haven't looked at yet, and we'll finish off with the method of substitution, which is the first sort of significant technique in finding antiderivatives, definite integrals, without using Riemann sums in the latter case. So, I'm sort of going to pick up where I left off last time. In fact, I'm even going to go a little bit behind, or rewind a little bit, and just remind you what we were looking at. So, we've been studying objects like this, the integral f of x with respect to x from a to b. And I just want to remind you that that meant we took the graph of f between a and b, and we found this area, or we want to say that this area is equal to this definite integral with the proviso that everything below the axis counts as negative. Okay, so this is a number. It's a number. An area, signed area. Once you, of course, specify a, b, and f. This is just a particular number. Okay, but it's kind of hard to calculate using the Riemann sums, right? This is not such an easy thing to do. We didn't really do any examples of it, just a little bit, but there is that example in chapter 16. There's got to be a better way, and there is, and we started looking at it, as I said. The real breakthrough is first to change the dummy variable to t, which doesn't really do anything important, but it does allow us to write a new function, or define a new function, capital F, with a variable x. We've got f of t dt. I can't use x here and up here, because that would be a conflict between the dummy variable. So the t is fine. We're fixing a, but the right-hand endpoint, x, becomes variable. And just to show you, just to remind you, if this is the graph of y equals f of x, we're fixing our point A. That's like a certain left-hand endpoint of a curtain. I want you to think of this as a sort of curtain rod, not a horizontal curtain rod in this case, but some sort of wonky curtain rod. And we're drawing this curtain that goes up to a point x. And x is what we can shift back and forth. So if I push this along, then I sweep out more area. So f of x measures the area up to x. So if I push x a little bit, x is the variable. If I take the same picture, a is still in the same place, and I push x a little bit to the right, so this is the new x, this area here, it's a bigger area in this case, would be what I've called f of x new. So I can shift x back and forth. And the question is, what can we say about this capital F? And since this is a calculus course, here's a function. What do we do with functions? We differentiate them. And it turns out that we can differentiate it. So f is differentiable, and its derivative is just the original function, little f, but evaluated at x. And I did state this last week. Since this is the derivative of f, which is this, we can also write it using the d dx notation as the derivative with respect to x of this weird integral function is just little f of x. And this is the first fundamental theorem, which I did state, as I say, first ft. Ft in this case is fundamental theorem of calculus, and it's true when f is continuous on a b and x in a b as well. So it might break down when f is not continuous. Sometimes it still works, actually. There's, well, there are certain you can improve it, but I will be happy with this case here where f is continuous. Now, why is that true? I'm not going to give you a real proof but it is instructive to see almost all of the proof with just one little detail which I leave to, what is it, section 17.7 or 17.8, I forget. Anyway, in order to see why this might be true, and it's a pretty extraordinary statement. Everything makes sense when you look at a picture. And you don't need to know this in Math 103 at least, why it's true. But I cannot show you something called the fundamental theorem without at least justifying it why it might be true, since all of integral calculus depends on this theorem. Okay, it is fundamental. This is the definition of the derivative of f. So what does it actually mean? Well, we have to take f of x plus h minus f of x. So what is f of x plus h? Well, here's our function little y equals little f. And now I've got my fixed endpoint a. And I'm going to take x here. I'm going to take x plus h. Okay, now, in green, that area from a to x is capital F of x. Whereas in the pink, if I go all the way up to x plus h, that area is f of x plus h. And what I'm interested in is the difference between the two. I want the pink area minus the green or yellow, whatever color it looks like. So that's the numerator of that fraction. So actually, the difference turns out to be this area here, just a fairly thin strip. So that blue area is f of x plus h minus f of x, which is the numerator of that fraction. Now let's take a look at this little strip here. The width of the strip is h, and the height at the left endpoint is f of x. Now, I agree the right endpoint isn't the same, but if the strip is really, really narrow and the function is continuous, then it's almost a rectangle. So the area of this strip, which is f of x plus h minus f of x, is approximately equal to the base h times the height f of x. In other words, forgive the blue now, I'll switch to white. I divide by h, that quantity is approximately equal to the height of that little strip, f of x. And so, when you take the limit, you need to use the mean value theorem for integrals, which we did do last week. I'm not going to do it now. As I say, 17.8, I believe, of my book has the actual details of it. But nevertheless, as h goes to 0, the strip becomes more and more like a rectangle. The right endpoint, in particular, this height, f of x plus h, becomes closer to f of x. And this approximation becomes perfect in the limit. So indeed, the limit of this equals f of x, which is exactly what we want. I left out the word limit here. Maybe we can revisit that, and at least I claim that this is true, and I've given at least a sanity check of it, as it were, some sort of rationale. Okay. So, just as a really quick example, this is actually an example from section 17.5. I'm going to come back to many more examples, but I just want to examine a specific example so you can get a flavor for it. If I write down something like this, the derivative with respect to x of the integral from 3 to x of sine t squared dt. If this derivative was not here, you'd have to try to do this integral. As it turns out, not a very easy integral. Basically impossible. So we have this integral here, but now I'm asking you to actually differentiate it. And it turns out that they undo each other. That's the whole point of this fundamental theorem. If you integrate and then differentiate, you get the original function back. In fact, you don't really have to do much work at all. You just have to take the integrand here, sine t squared, and change the t to an x. And that is the answer, sine of x squared. It looks like magic. But if you differentiate the integral, you get the original function back. Be careful of the variable. Now, when I say you differentiate the integral, of course, it's not just any old integral. It's got to have the right-hand endpoint being the variable that you're differentiating with respect to. Okay, so this looks pretty weird. But all it says is, if I consider the area under this curve from 3 to x, and I wobble x around a little bit, then the change will be sine of x squared itself. That's how much the area changes when you wobble the right-hand endpoint. So everyone looks at this, basically everyone looks at this and says, what about the 3? Surely the 3 must make a difference. Okay, this is the real sticking point with this theorem. Well, I want to come back over here. Let's just, I'll obscure that for a second. I want to come back over here and just consider, I'm considering the change in area. How much does the area of this curtain change as I shift this left and right? I don't care what the area actually is. I just care how much it changes. So it actually doesn't matter where it starts. It's only what's going on around here that matters. So put another way, suppose I actually started at some other number over here, say capital A. And f of x now, I'm always adding that shaded area here to the value of f of x. So I've increased f by a constant. Of course, its derivative doesn't change. And in this example here, if I did the same thing for the new value, the difference between these two, that's how you see how much something changes, is the same as the difference between the original two. Because I'm just taking away this extra bit of curtain that's the same in both places. So actually it makes a lot of sense that this endpoint at the left doesn't matter. You want to know how much the area changes? You don't need to look all the way over there. You only need to look at the bit of the curtain that's near where you're changing it. So although it seems whacked out, mysterious, weird, actually, if you understand what it means, it makes some sort of sense. Now I'm going to do some more problems based on the first fundamental theorem. But I'm kind of on a roll with these theorems, and I need to show you the second fundamental theorem. The good news is there's only two. There's only two. And the second one, I have to tell you, is the one that's really, really useful. The first one's kind of cute. You can solve some problems, but this isn't a very natural thing to look at, actually, d dx of an integral like this. It turns out the second fundamental theorem is the useful one. And in order to set it up, remember, we are often trying to find an integral that looks like this, integral of f of t dt. Okay, now, actually, in terms of the capital F that I had set up before, this is just f of b. See, after all, f of x, capital F of x, that is the same thing, but we're going from a to capital X. Okay, so that's a nice little observation. Now, another observation I'd like to make is, what's this integral here? The integral from a to a of f of t dt. Well, this, of course, is f of a, but as we saw last time, if you integrate from a to a, that's nothing. That's nothing. That's like the area of this line, and lines don't, or line segment. Line segments have no area. So this is 0. So the integral we want is f of b. And the integral, and here's another value that we know, f of a. Now let's just bear these things in mind. What do we know about capital F? Capital F is a function whose derivative is little f. So we know capital F of x, its derivative is little f. So in terms of little f, we'll say that capital F is an antiderivative of little f. It's an antiderivative. It's the opposite of a derivative. Not quite the opposite. It's really the inverse procedure. Instead of differentiating, we find the function whose derivative is the one we started with. Now, when I say find the function, of course, there's not just one antiderivative, and we discussed this last time. If you add 3 to any function, its derivative is the same. If you subtract 17, it's the same. You can add constants and still be an antiderivative. So Here then is our prescription. We want to start off with this integral here. Suppose we pick any antiderivative. Suppose g is any antiderivative. I don't know which one. They all differ by constants anyway, of little f. Okay, so we have this antiderivative. If we can find one, my point is it doesn't matter which one we use, as long as you get the formula right. What do we know? We know that capital F, defined in our way, well, it was defined on the previous board. We don't need to scroll over it. We know that capital F is an antiderivative. G is another antiderivative, so they must differ by a constant. G and F are basically the same function, but shifted up. Okay, we also know f of a equals 0. So if I write down g of a is f of a plus c, then f of a just goes away. It's 0. So we now know what the constant is. It's g of a. So if you plug this into that equation up there, you get that g of x is equal to f of x plus g of a. In other words, f of x equals g of x minus g of a. Sounds like we're just playing games here, but I'm almost at the conclusion. You see, f of b then, if you plug in b, you get g of b minus g of a. And if we go back now, there's one equation that I just wrote up. Go back to the very first equation up there. That's what we really want. We want to find that integral from a to b of f of t dt. So we know it's f of b. We just found out what f of b was. It's g of b minus g of a. So we've proved a nice formula, but what does it mean? Well, what it says is, you want to find this integral, right? What you do is you find your function capital G, which is any antiderivative of f. You just have to find an antiderivative of f, g. It doesn't matter which one you use. As long as you calculate that, you found your integral. Now, it's normally changed, capital G is any antiderivative. So I'm going to forget about the old f, which was just one antiderivative, a very special one, defined by that integral, and I'm going to rename g into f, just because it's sort of cleaner. And I'm going to change the dummy variable from t to x. None of those two things, neither of them makes any difference at all. It's just I'm trying to get in line with the standard way of stating the second fundamental theorem, and here it is. Well, let me state it so I can put a box around it. So if capital F, and that could just be g if you prefer, is any antiderivative of a continuous function f, and it's continuous on, say, a, b, then the integral of little f of x dx is just capital F of b minus capital F of a. And that's the theorem. That's the second fundamental theorem. It's not inconceivable, at least for Math 103, that you might be asked to state this theorem. I've seen it before. It's pretty rare. Normally you have to apply it. And, of course, in other universities or schools, who knows what happens. Anyway, the right-hand side is often written like this. You write f of x, and you put this big vertical bar. You write a, b. That just is a shorthand for writing f of b minus f of a. Okay, it looks weird, but it's just a simple, short way of writing this. Of course, if you actually want to calculate this, you have to expand it like that. So this is a pretty nice theorem. It's a pretty nice theorem. And, you know, I looked at this example last week. Let's just try it again. We're going to find the integral of x squared dx. from 1 to 2, I'll just redo this. I need to find an antiderivative of x squared. What is a function whose derivative is x squared? Well, if you think about it, x cubed over 3 will do. Because when you differentiate this, you get 3x squared divided by 3, which is just x squared. But of course, this is not the only antiderivative. I'm going to choose another one by adding 1,000 to it and show you that it doesn't matter. So this, certainly the derivative of this is x squared. Now, according to the fundamental theorem, I need to evaluate this between 1 and 2. Okay? I need to take this expression when x is 2 and subtract the same expression but with x equals 1. So that is 2 cubed over 3 plus 1,000 minus 1 cubed over 3 plus 1,000. And it's important that you put these parentheses here. It's got to be all of this when x equals 2. If you forget the parentheses, you get your minuses and pluses all wrong. Anyway, what you see is you get 2 cubed over 3, which is 8/3, minus 1/3, and you see that the 1,000s just cancel out. They just cancel out. So it actually, you could change it to 1,000,000 and they would still cancel out. You could change it to minus 72 and they would still cancel out. So that's why the constant doesn't matter, because it's embedded in both of these and you're subtracting it, so they cancel. They cancel. You can use any antiderivative. Anyway, the answer in this case is 7/3, and that is a hell of a lot simpler than using Riemann sums. So this theorem is pretty important. You can't really do integration without it. You'll just be hamstrung. All right, so those are the two theorems, and they are pretty important in humanity's development in a way. I don't want to get all philosophical here, but they are, of course, central to the study of calculus. So actually, inspired by the second fundamental theorem, I'm going to show you a new notation for antiderivatives. It's going to be called an indefinite integral. We've seen definite integrals. Every integral we've looked at so far is a definite integral. Okay, so we've seen this. This is called a definite integral. And remember, it's an area, or a signed area, so it represents a particular area, as I've drawn up before. So for a given function f and numbers a and b, this is a number. Now, according to the second fundamental theorem, the way to compute this is to find an antiderivative of f, if you can. So inspired by this, it's very convenient to, instead of writing an antiderivative of f, to have a symbol for it. And because of this connection, we'll just write integral of f of x dx without bounds here, or endpoints of integration, or limits of integration. These are blank. And this is an indefinite integral. And it doesn't represent an area at all. It's antiderivatives of f. Which ones? All of them. So it's actually a family of functions. And it's a very close family. They're all the same function, except that they differ by a constant. So in particular, or for example, the indefinite integral of x squared dx is x cubed over 3 plus c. And this plus c means it's a constant, and it's an unspecified constant. So I don't know what it is. In fact, it's not that I don't even know what it is, it's that I'm allowing it to be anything. So what this means is all the antiderivatives of x squared are given by x cubed over 3 plus some constant number. So it tells you that, for example, x cubed over 3 plus 7 pi is an antiderivative of x squared. It's one of them. Okay, so I just want to really stress that here you get some functions, whereas if I went from 1 to 2 and I got 7/3, there you get a number. It would be moronic, insane, to use this same notation for areas under curves and antiderivatives if it were not for the second fundamental theorem, which says that actually to find this, you use this fact and just plug in 2 and 1 and subtract. And it doesn't matter what you use for c because it will cancel out when you subtract. So indefinite integrals, you're just looking for functions whose derivatives are the function you started off with. But this is not such an easy thing to do. Derivatives are hard enough, but to undo the operation, I mean, in this case, you know the derivative of x squared is 2x, but that's not what you need. You need the antiderivative, and you have to sort of think backwards. X cubed, yeah, I know it's 3x squared. But if I divide by the 3, I get the original thing back. Anyway, now that we have this, I want to just state one equation which summarizes this. And it's so important, I really, really want you to learn this. If the derivative of some function capital F of x is equal to little f of x, then the integral, the indefinite integral or antiderivative of little f is capital F plus constant. That is nothing more than the definition of antiderivative, and yet it's amazing how useful it actually is. So for example, we know that the derivative of, say, sine x is cosine x, which immediately allows you to reverse this and say the integral of cosine x is sine x plus a constant. By the way, that's a very often, well, this is often done wrong. The derivative of cosine, yes, is minus sine, but the integral is actually plus sine. And the reality check as you look at this equation is you say, oh, what's the derivative of sine? Cosine. That's the reality check. Just like if we come over here, I write down an equation like that, the reality check is that when I differentiate this baby here, I get this. Differentiate x cubed over 3? Yes, I do get x squared. Okay, so you have to be very good at changing between these things. Now, there's not that much to say about antiderivatives in indefinite integrals in terms of theorems. Remember, we had all these ideas about splitting up integrals that I did with definite integrals. You can't do any of that with indefinite integrals because there's nowhere to split. It's not an area. It's just an antiderivative. So basically, the only things that are even worth saying, which are more or less obvious, is that if you want to find the integral of f plus g, indefinite integral, that's the antiderivative, well, this is just, you can split it up into the integral of f plus the integral of g. And that's just because the same is true with derivatives. If you have a sum of two things and you take the derivative, you just add up the two derivatives of each piece. Well, the two derivatives, one of each piece. So there's no sum rule. Similarly, constants can go in and out. If you find the antiderivative of the constant multiple, the constants can come in and out. This is only true if these are constants. Maybe I should use a little c here so that we don't get confused with the plus c. All right. Well, that's quite a lot to think about there. Wonder if there are any questions about all this theoretical stuff that I've been doing. I'm about to embark upon some examples, but perhaps you have some questions. Well, let's do some examples. So I'm going to start off with problems based on the first fundamental theorem, which belong in section 17.5 of the Calculus Lifesaver. And then I'll move on to problems based on the second fundamental theorem. Okay, we already saw one example of the first fundamental theorem. Let me show you another one. Suppose I take d dz of the integral from minus e to z 2 to the power cosine, what do I want here? W squared log w plus 5 dw. Okay, don't even think about trying to do the integral. You'd have to find an antiderivative of 2 to the cosine w squared log w plus 5. What a mess. Don't even think about it. Because, again, you're just going to take the derivative of it anyway, and the two things undo each other. It would sort of be, I don't know, it's sort of like saying, suppose I take the square root of 1, 2, 3, 4, 5, 6, and I ask you to square that. Why would you even try to calculate the square root when you know that if you take a positive number, you take the square root and then you square it, you just get the original number back? That's exactly the same sort of thing we're doing over here. This is going to undo that, and in fact, you just have to be careful of your variables. You just take this integrand here, but replace the dummy variable w by the actual variable you're differentiating with respect to, which is z. It is wrong to put w. There is no w. W does not exist. It's a dummy variable. It's also wrong, and I've seen this many times, to put a plus c. There's no plus c. When you differentiate, that's what we're doing here, d dz of something, there's no plus c. I agree, if you were going to work this out, you might think there was a plus c. Actually, even as a definite integral, there shouldn't be a plus c. But even if it was a sort of indefinite integral, there would be a plus c, but when you differentiate it, it would go away. So this differentiating means no plus c. So it's actually an error to put a plus c, and it's an error to put w's in this case, because w is the dummy variable. Okay, so be careful. There's also an error to do any finding of antiderivatives, because you can't. Or I don't think you can. I wouldn't have a clue how to start. Okay, so any questions about that example? Yes? Very good. So here is the basic type. It works when the top is just the same variable you're differentiating, and the bottom is a constant. Now, I know it's not just a number like 2, but actually e is a number, minus e is a number. It's about minus 2.718, etc. So this is constant. So the prototypical type where we can just use the theorem directly is where you've got a constant up to the variable itself. But I'm actually going to look at 4 variations along the lines of what you asked there. What if these things are more exotic? So everything is going to boil down to this case right here, but we're going to look at some variations after these messages. That'd be cool if we could edit in some ads here so you don't have to just watch me erase the board, huh? And I could sell advertising space in the book as well. I don't know what you'd advertise in a calculus book. Maybe a multivariable calculus book? Who knows? Okay, let's look at variation 1. So the simplest change I can think of is where the variable is on the bottom of the integral, which is the left-hand endpoint, or left-hand limit of integration. For example, suppose I go from x to 7 of t cubed cosine t log t dt. Well, I guess here x had better be positive, by the way. I'm not paying too much attention to this, but I can hardly take the logarithm if it's not positive. So anyway, not worrying about that. I can't just write this down like I did because the x is on the left-hand endpoint. But there's a simple thing you can do. Remember, you can switch the bounds of integration if you put in a minus sign. So this is d dx of, without even doing the derivative, I'm just going to handle the integral first. I go from 7 to x. And now the x is in the right place. Of course, I've got a minus, but that just comes straight out through the derivative. And so now I can just take this integrand, change t to x. Don't forget about the minus, and I get minus x cubed cosine x log x. Not plus c and no t. It's all x. So the only difference in variation 1, where the variable's on the left-hand endpoint, you've got to switch the bounds but introduce a minus sign. Okay, so now I fixed the right-hand endpoint of the curtain, and I'm moving the left-hand endpoint. And the reason you've got a minus, by the way, if you fix the right-hand endpoint in this picture, if you fix the left-hand endpoint, in this picture, if I move the curtain to the right, the area increases. Whereas if I fix the right-hand one and now move the left hand to the right, the area decreases. I've got less curtain. So that's another way of looking as to why you need the minus sign. The area is getting smaller, not bigger. Okay, any questions about variation 1? This is along the lines of what you were thinking, right? But we can make life even more complicated. And I'm sorry to say, at least in Math 103 exams at Princeton, they very often do. So let's look at variation 2. Okay, variation 2 is where you have not just x, but some function of x. Let's look at this example. Suppose I take d dx, I'm going to go from 0 to x squared. Not just x, x squared. And some integrand here, which I seem to be choosing fairly nasty integrands, just to dissuade you from actually trying to find antiderivatives here. So I have inverse tan t to the 7 plus 3t dt. That's not the interesting part. The x squared is the interesting part. In order to deal with this, I have to use the chain rule. So we could almost write down the answer, but I think that it would be wise to be prudent here. We want to find the derivative of something. Let's call that y. In order to find this, instead of just going with equals, I'm just going to set y is the integral from 0 to x squared. Inverse tan t to the 7 plus 3t dt. And what are we actually looking for? Well, this is just the derivative of this. So we need dy dx. All right. X squared is making our life miserable, so let's substitute. Let u equal x squared. You could use any variable here, but I would strongly suggest do not use t, or else you'll get completely confused. T is a dummy variable. You don't want to use dummy variables outside of the integral. So u equals x squared. If we do this, y is simply the integral from 0 to u. We've gotten rid of the square, but we had to change the variables in order to do it. Inverse tan. Okay, so I haven't really accomplished much so far. Better do a derivative or two. If u is x squared, we can write down du dx easily enough. It's just 2x. And we can write down dy du by using the fundamental theorem in its variation, without the variation. In fact, just plain, simple. Dy du is just this expression, the integrand, but with t replaced by u. It's just the plain vanilla first fundamental theorem type of problem, but instead of x, I've used u. Well, a u shouldn't faze you. I mean, I just did an example over here with w's and z's, and, there's no problem. We don't need to linger on this, but, just remember that not everything is an x. So in this case, I'm going from 0 to u, and I'm differentiating with respect to u. Okay, well, now we just use the chain rule. dy dx, which is what we want, is dy du du dx, that's just the old derivative chain rule. Forget the integrals, that's all it is. And we found both of these quantities. dy du is inverse tan u to the 7th plus 3u. And du dx is 2x. All we have to do is get rid of these u's, go all the way back to x's. And since u equals x squared, this is x squared to the 7th plus 3x squared. And we can write this as 2x inverse tan x to the 14th plus 3x squared. Another way of looking at this, of course, it's conceivable that you could just write this straight down. Look back over at the original problem. All you have to do is plug in x squared instead of t, and then multiply by the derivative of x squared. That's the shortcut. You replace the dummy variable t by x squared, but then multiply by the derivative of x squared. That's all we've done in the chain rule. So we can do another example. I'll do it that short way, but then I'll show you the long way as well. So here's another example. d dq from 4 to sine q, not just q, but sine q, tan of cosine of a dA. So there's no x's anymore at all. Well, the short way, and perhaps the risky way, because if you get it wrong, there's no working. I'm just going to write down the answer. All you do is replace the dummy variable a by sine q. So the answer should be tan cosine sine of q. But because it's not just q, it's sine q, I also have to multiply by the derivative of sine q, which gives us a cosine q. There's no plus c, and there's no a. Do you believe it? If not, let's let u, here's the gory details of how I got this. U equals sine q, and I'm going to call this expression here y. I'm not going to write it out again. I've got to leave something for you, although this is all in section 17.5. I guess it's 3. Sorry, I don't have the exact reference, but it's variation 2 within 17.5. So if I call this y, then y is equal to the integral from 4 to u, because I've changed sine q into u. And I get tan of cosine of a, and of course dy du, by the fundamental theorem, is tan cosine of u, and du dq is cosine q. So this expression is supposedly dy dq, be careful of your variables, is dy du times du dq. dy du is none other than this, because it's tan cosine u, and u is sine q. And here's du dq, which I got from over here. So I've been a little bit sparse in the writing down of the full solution, but hopefully you can go over it at your leisure. So variation 2 is a lot harder than variation 1, but there's still the potential of writing down the answer straight away. Any questions about that? If you have one, I think you can shout it out as I make some space to show you some more variations. So, any questions? All right, well, before we go on to variation 3, let me just point out you could have variations 1 and 2 together. For example, let's just change that last question very slightly. Instead of going from 4 to sine q, I'll go from sine q up to 4. Again, of tan cosine A dA. Well, of course, you've still got a function here of q in this case, but it's on the bottom. It's on the left-hand endpoint instead of the right-hand endpoint. So we need to do variation 1 first. And switch them around. Go from 4 to sine q. But you've got to introduce the minus. Then solve the problem the rest of the problem using the chain rule like we just did, and you'll get the same answer as we did before. Tan cosine sine q times cosine of q, except that you'll have the minus from the variation 1. Okay, so it's almost the same. It's almost the same. Any questions about that? Well, variation 3 is the last of its kind. There is a variation 4, but it's a completely different type of problem, apparently. So let's just consider this. Derivative, d dx, of the integral from x to the 5th to x to the 6th of log t squared minus sine t plus 7. Actually, in this case, it doesn't matter what t is. T squared is positive. Sine t is at most 1. So inside we have at least 6. So you can take the logarithm. Anyway, so we like to do variation 2. But first we've got to decide whether we can use variation 1. Maybe we need to put a minus and switch these. No, still no good. We've got x's both here and here. So the way to deal with this, variation 3, is when you have x's in both places, or whatever the variable is. In this case, it's x. So what do? You pick your favorite number, as long as it's in the domain here. You don't want to get out of that. In this case, the domain is everything. So you pick your favorite number. Doesn't matter what it is. Might as well be 0 most of the time. That's in the domain. Well, I don't know about most of the time. Whatever. I'll pick 0. I'm going to split the integral up before I even differentiate. I'm going to go from x to the 5th up to 0, or 1, or minus 7, or whatever you felt like putting there. So I'm going from x to the 5th up to 0. Then I have to go from 0 up to x to the 6th, and that of the same quantity, and that will complete the integral. And you're allowed to do this. We discussed this last time. Question?
It's always plus between those two?
It's always plus, provided that you start at the left endpoint of the original, go up to your new point, and then start from the new point up to the old one. That's how I actually stated it last time. You can go from A to B is the same as going from A to C plus C to B. Right? I mean, think of it this way. If 0 happened to be in between x to the 5 and x to the 6th, which it could be, for example, if x is negative, then this would be negative and the other one would be positive. And if you want to go all the way from the left to the right and you break it up somewhere in the middle, then the total is the sum of going from the first to the middle and then from the middle to the end. Okay, but as you point out, I'm just going to flip this one anyway because this is a variation 1 plus 2. That one I'm going to leave as it is. So the first thing I'm going to do, I can split up the derivative into 2 bits. And then the first integral, I'm going to use variation 1 to flip this around with a minus sign. Now, if you feel comfortable writing this down as it is without further ado, then by all means write down this in one step. But I think it's safer to do it the way that I've stated it. And the second one I don't touch. Okay, so just to reiterate what we did, our original thing, we busted it up into x to the 5 to 0 plus x to the 0 plus 0 to x to the 6th. The first one was the wrong way around, so we flipped it with a minus sign. And the second one we didn't touch, except that we realized that we're differentiating so you can break up the derivative and do each piece. Now, I encourage you to use the chain rule in the way that we did. They're both variation 2. I'm going to be a little bit briefer. I've got the minus sign from up here. I'm just going to take this integrand, and where I see t, I'm going to put x to the 5. So I'm going to put t squared is x to the 10 minus sine x to the 5 plus 7. And now I've got to use the chain rule in a way of multiplying by the derivative of x to the 5. So that takes care of the first derivative, well, the first piece. And the second piece, I've got log of, now instead of t equals x to the 5th, I put x to the 6th. So I'll get x to the 12 minus sine x to the 6 plus 7. And I need to multiply by the derivative of x to the 6, which is 6x to the 5. And again, I'm just writing down that answer, but I really think it's a good idea to use the chain rule in a way that I did when I did variation 2. So in summary, variation 3, split up the integral, take the first piece, variation 1, flip, and then use variation 2, the chain rule type of thing, to do each piece individually. And those ones are pretty tricky. So you need to practice these things. It may be that if you're watching this online from a different school, these problems don't even come up. But I certainly know that at Princeton I've seen this type of problem. And I think it's fair game. But they are a little bit abstract and arbitrary, and they don't really come up in the real world. They're sort of a game to make sure you understand the first fundamental theorem. Soon I'll do problems involving the second fundamental theorem, which come up all the time. That sort of stuff comes up all the time in reality. But I have a question.
And you just said you have to make sure the number you fix in the domain of like the t equation.
Yeah, I mean, if the function looks like this and is undefined anywhere else, and you want to split up this integral over here, say, then you're trying to say this integral here is the same as this integral from there to there, which would have been negative if this function was like this, plus this, which would have been positive, except that this doesn't even exist, because the function's not even defined here, and this doesn't exist, because you can't even go up to there, so you just fail. But that's a technical sort of point. I mean, actually, I have to say that if I were grading this, and you picked 0, and 0 didn't happen to be in the domain, I mean, you know, you might lose a point out of 10, or maybe no points out. You might even still get full credit. But technically, yes, it's supposed to be in the domain.
We just had I was just looking at the homework problem, and there's one that's just the log of t. So you pick 0 there, not the domain.
Yes, so if you had the log of t instead of log of t squared minus sine t plus 7, pick 1 instead, or something like that. As I say, I mean, most of the time you wouldn't even lose any points, but you wouldn't be doing it correctly. Actually, with log of t, you can even pick 0, but then the function, it becomes an improper integral. And if you want to know more about those, you have to either take Math 104, or if you're watching online, wait a few lectures. It'll be next year for me, but hopefully they'll all be up, and you can learn about improper integrals, and yes, that would work. You just couldn't go negative. Good. Any other questions about any of these variations? There's one more variation of problem that I can think of. Of course, there's always more variations. I just try to do the most common ones. Variation 4 is not even a derivative. It would be something like this. Consider this limit. Limit as h goes to 0 of 1 over h, the integral from x to x plus h, log 3, or base 3, of cosine t to the power 6 plus 2 dt. It's not even a derivative. It's a limit. Well, well, it's a limit, but yet it's just a derivative. In fact, it's a derivative in disguise. In order to deal with this, instead of writing equals, just set f of x is the integral up to x of this nasty thing, log cosine to the 6t plus 2 dt. Where do I start? Doesn't matter. Anywhere in the domain. Again, I'll pick 0. Well, no, 0 is boring. I'll pick 1/3. What the hey? Doesn't matter. This is anything in the domain, again, of the integrand, which in this case, again, is anything, everything. Okay, so if I set f of x equals this, what is this limit? Well, this limit is the limit as h goes to 0 of, well, it's 1 over h, f of x plus h minus f of x. Do you believe it? With this is equal to f of x, do you believe that this integral just going from x to x plus h is equal to 1/3 to x plus h minus 1/3 to x? Maybe it needs some proof. Maybe it needs some proof. I better squish it in over here. If you look at f of x plus h, that's the integral from 1/3 up to x plus h of this nasty expression. Now, we can split this integral up as follows. We'll go from 1/3 up to x of blah, 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 plus the integral from x up to x plus h of the same thing. Just stare at that for a second. F of x plus h, we're going from 1/3 all the way up to x plus h. We can just go from 1/3 up to x, and then from x up to x plus h. And this quantity here is just f of x. So if you bring it over to the other side, you get f of x plus h minus f of x is this integral which we want. That is the integral over here. And then you just have to divide by h because the question asks for it. The point is that this is just the derivative of f, capital F. But by the first fundamental theorem, this is just the derivative of this integral, which is the integrand. Finally, I get to write, man, I'm being aggressive with this chalk. I get to write the integrand, but with an x and no integral. Tricky stuff. Tricky stuff. Derivative in disguise. Actually, another thing you could do in this problem is you could use L'Hopital's rule, believe it or not. You could put this h down as a big denominator, and it's a 0 over 0, and you could differentiate with respect to h and use variation 1. It's a sort of a variation 2. You're just differentiating with respect to h there. And that will work too. It's an interesting exercise. But this is sort of the more classical way of doing it. So you may have to stare at that. Nasty problem. But it's actually using the proof of the first fundamental theorem, because in the proof we did look at this quantity here. Remember, I drew those different colored regions and subtracted them. That's actually what we're doing over here. So any questions about this variation 4? It's the final variation, the derivative in disguise. Well, if you have it, as I'm erasing, again, holler it out, please. Well, no questions, so let's look at some problems involving the second fundamental theorem. And as I was saying, this stuff is pretty useful. This is how to find integrals. And as we know, you've got to find antiderivatives. Now let's look at a whole bunch of examples. So these come from 17.6. My plan is to spend about 10 minutes looking at examples of this, then look at some other stuff about finding areas. We've already done a little bit about that. And then I'm going to spend the last 40 minutes or so on substitution, which is the last topic for Math 103. Okay, so before I do problems on the second fundamental theorem, as I said, you need to be able to find antiderivatives. So if you try to find the antiderivative of x to the a, it should be x to the a plus 1. Because after all, if you differentiate this, you get a plus 1 x to the a. So all you have to do is divide by the a plus 1. And everything will cancel out. When you differentiate, the a plus 1 cancels, and you do get x to the a. The only thing is, you better add a constant. And a had better not be equal to minus 1. So this is a very useful formula. If a equals minus 1, of course, you'd have a 0 on the denominator. So what happens when a equals minus 1? We want to find the integral of 1 over x. Well, I'm going to tell you what the answer is. It's log of the absolute value of x. Maybe you think it should just be log of x. Well, because after all, we do know that the derivative of log x, we found this out a few weeks ago, derivative of log x is 1 over x. So this should mean that the integral of 1 over x is log x. The problem is, this exists for all x apart from 0, whereas the left-hand side only makes sense for x positive. So actually, if we take log x, it looks like this. But if we want to take the mirror image like this, so that this is exactly a mirror image in this line, that's what log of absolute value of x looks like. So this is an even function. Its derivative is an odd function. And since it's 1 over x on the right, it must be 1 over x on the left. That's an odd function. So that's not a proof. There is a proof in in section 17.6. But in any case, the thing that you should learn is this boxed formula here, for sure. Now, those are the two non-obvious formulas. What I mean by non-obvious? Well, the others all follow directly from the integration. Now, if you look in the Calculus Lifesaver on page 373, unfortunately, that's not the page reference in the copy that you have, and I actually don't know what it is, and I apologize. But if you look in 17.6, and actually, if you do have the Calculus Lifesaver, a paperback version of it, it's on the inside back cover. There is a table of derivatives and integrals that you should learn, and they are the most important ones. And they include these two, but have all the exponentials and the trig stuff as well. So I'm not going to write it all out because you have it right there. As I say, these are the two most important ones. Good. So, having said that, let's look at a couple of examples. Suppose you want to find this. Well, this is in the table, but without even thinking about it, what function has a derivative of secant squared? Tan x. Okay, so that's just on the table, and it's, as I say, derivative of tan is secant squared, so this integral of secant squared must be tan x. Now, what if I change this to secant squared 7x? Okay, you can do this by substitution, which I'll do in a little while, as I said, but actually, you can do it without substitution. What happens if you differentiate tan 7x? It's just a multiple of x. so the 7 comes out. The derivative of this would be 7 secant squared 7x. We have to kill that 7 by dividing. Indeed, the derivative of tan 7x would be secant 7x times 7, but then we would divide by the 7. So it's the opposite. When you differentiate with a constant multiple of x, you multiply. But if you integrate with x replaced by a constant multiple of itself, you divide by that. Here's another example. What would the integral of e to the x be? Well, it's just e to the x. After all, the derivative of e to the x is e to the x, so of course the antiderivative of e to the x is e to the x plus a constant. So what if I replace x by minus x over 3? Well, you can think of this as multiplying x by minus 1/3. I've replaced x by x times minus 1/3. So I'm going to divide by minus 1/3, which of course is the same as multiplying by minus 3. Reality check, differentiate this, you get e to the minus x over 3 times minus 1/3. The minus 1/3 kills the minus 3, and you just get e to the minus x over 3. Okay? Here's an even more exotic example. Suppose I try to do dx over 1 plus 2x squared. Well, I want you to think of this as dx over 1 plus root 2x all squared. After all, if you square root 2x, you get 2x squared. So this should remind you, I'll leave this blank for the moment, what's the integral of 1 over 1 plus x squared dx? You can put the dx on the top if you like. What function has that derivative? Inverse tan, arctan, same thing. So given that formula, all I've done is replace the x by root 2 times x. So this is going to be 1 over root 2. We've got to divide by root 2. Inverse tan of root 2 times x plus a constant. That's this follows. Okay, no substitution needed. Just write it down. Okay, so those examples are not really examples of the second fundamental theorem at all. Those are examples of finding antiderivatives, right? The second fundamental theorem tells you how to find definite integrals using antiderivatives. So, I'm going to look at some problems. Consider this. Integral from minus 1 to 2 of x to the 4th dx. Very simple example, but it contains a slight trap for the unwary. All you do is you use the formula right at the top of this board, but instead of a, we're going to use 4. So if we do that, we're going to take the antiderivative, x to the 5 over 5. You add 1 to the exponent, then divide by the same thing. You don't need the plus c. You just need to put this vertical line and go from minus 1 to 2. So the only trap is to make sure you put enough parentheses. Take big-ass parentheses there if just need be. Replace x minus 1 to the 5 over 5. And all you have to do is make sure that you get a minus a fifth, which is 33 over 5. And so that's actually the area on the curve x to the 4th, y equals x to the 4th, between minus 1 and 2. We didn't even need to draw the graph. We didn't need to do a single geometrical calculation at all to find an area. All right. How about this one? The integral from minus e to minus 1 of 4 over x dx. Well, we know the integral of 1 over x That was also on the top part of the board. Maybe we can just look at it for 1 second. It's the second line there. It's just log of absolute value of x plus constant. So if we come back down here, this is 4 over x. 4 is just a constant. So it can come out 4 times 1 over x. So you can just write it down as 4 log of absolute value of x. You don't need the plus c. What you need is to go from minus e to minus 1. And make sure this line is big enough so that you don't confuse it with the absolute value here. If you do this, you get 4 log absolute value of minus 1. It's minus 4 log absolute value of minus e. So you go from, you take the right evaluation minus the left evaluation. And you get 4 log 1 minus 4 log e. Log 1 is 0. Log e is 1. So this is negative 4. Does that make sense? We're taking the curve y equals 1 over x. We're going from minus e up to minus 1. That area there is minus 4. Does that make sense? Yes, it's a signed area. We're below the axis, so it should be negative. It should be negative. On the other hand, if you went from minus 1 backwards to minus e, you get a positive number. And I discussed this last time as well. If you integrate a negative function backwards, it's like you're playing a backing up car in reverse, and it looks like it's going forward. So it should be positive. All right. A couple more. Any questions? These things do come up all the time, not just in pure math, but in applied math, physics, engineering, all over the place. Medicine, economics for sure, and probably many other disciplines. Certainly science all over the place. All right. Let's do this one. I'm going to skip one from 17.6. Actually, I'm going to skip 2 of them. I'm just going to do one more example, lest I run out of time. Suppose I want the integral of dx over x root x from 4 to 9. Well, the trick here, it's not much of a trick, is to write the integral as x to the minus 3 halves dx. The integrand is x to the minus 3 halves. Make sure you believe that x to the minus 3 halves is the same as 1 over x root x. Just straightforward index notation, but you've got to be able to do that. So according to the rule, you add 1 to that index, or to that exponent, and you divide by that quantity. So it's x to the minus 1 half divided by minus 1 half. And we're going to evaluate that from 4 to 9. And it will be clean to write this minus a half on the denominator as just a minus 2 in the numerator from 4 to 9. So let's just make sure we get this right. Big parentheses. Minus 2 times 9 to the minus 1 half. Minus 2 times 4 to the minus 1 half. You need this minus, which comes from the fundamental theorem, but you need these 2 minuses, which come from the antiderivative. I don't know why that's a third there. It's mysterious to me. Should be a half. I also don't know why I put loops on these 3 2's and not that one. I cannot explain that, but they're all 2's. This is the square root of 9, reciprocal. The reciprocal comes from the minus. So this is minus 2/3 minus, and the same thing, this is 1 half, minus 2 halves, the square root of 4, and the reciprocal. So this is 1 minus 2/3, so it should just be 1/3. Okay, so to do definite integrals, find antiderivatives, find an antiderivative, don't put the plus c, and evaluate at the right endpoint minus the left endpoint. Okay? No questions? Well, just want to look at two area problems, and we looked at a little bit of this last time, but now we have this fundamental theorem. We can do some fancier examples. So you might recall last time I looked at the integral from minus pi to pi of sine x dx. And the graph of this so here's y equals sine x just from minus pi to pi. It's supposed to go through the origin. I just can't draw. We decided this integral is 0 because that's an odd function. So everything below here is the negative of everything above here, and whatever this is cancels this out. And that's all beautiful. And in fact, we'll come back to that relation right at the end of this class. And I come back to integrals of odd functions. But what if you actually want the unsigned area? I want this area. I don't want 0. I want to know what is the physical area that you're looking at. Well, as we discussed, that's the same thing as taking the absolute value of it first. If you take the absolute value, it flips all the things below into things above. So that's the area that I want. So actually, what I really want to do is go from minus pi up to 0 and from 0 up to pi. Let's just go from 0 to pi of sine x and find out what this is. According to this, I need an antiderivative of sine x. Does anyone in the room have a good candidate for an antiderivative of sine x? Negative cosine x. Why is it negative? Because the derivative of cosine x would be minus sine x. So you need the minus in here to make it work. That is a very, very common mistake I have seen students make in grading their papers. Integral of sine x is not cosine x. It's negative cosine x. Anyway, so if you put minus cosine pi minus cosine 0, cosine of pi is minus 1. So this is minus 1 minus 1. Cosine of 0 is 1. So if you've gotten the minuses the correct way, this should be 1 plus 1, which, as we all know, is 2. So this area here is 2. Now you can repeat the computation from minus pi to 0. Good exercise. Of course, if you go from minus pi to 0, you're going to get negative 2. You're going to get negative 2. It should be 2 in area, but it's below the axis. So in other words, what I'm saying is I leave it to you to check that if you do the same integral sine x dx from minus pi to 0, you should get negative 2. And of course, when you take the absolute values, it becomes 2 and 2. So you need to take, if you really want the absolute value of the whole lot, you split it up to where it's negative, where it's positive. So here's the computation of the actual area. Absolute value of sine x, I go from minus pi to 0 of sine x. And I take the absolute value of that, and then I go from 0 to pi. And I take the absolute value of this one as well. Of course, I don't really need this one since it's positive. Get the absolute value of minus 2 plus the absolute value of 2, which of course is 4. If you leave out those absolute values, you will get 0. That will give you the signed area. Okay, so the actual area in either of those pictures above that I had is 4. Questions about that? It's a pretty straightforward example. Let me give you one that's slightly less straightforward. Suppose I take the curve y equals 1 over x, and I take the line y equals x. I want to go from 1/2, which is around here somewhere, to 2. So I'm going to draw this vertical line in here, and this vertical line, x equals 2. And for some reason known only to myself, I'm interested in this shaded area here. So what is that shaded area? Well, from what I said last time, if you want the area between two curves, you take the integral of one curve minus the other. You really want the top curve minus the bottom curve. See, it's tempting just to take the integral from 1/2 to 2 of, say, 1 over x, that's one of the curves, y equals 1 over x, minus x. Or perhaps we should even do it the other way around. X minus 1 over x. See, x is on top of 1 over x, right? Well, not quite. Over here, 1 over x, the curvy one, is above the line. So, as I discussed, that's going to give the wrong answer because it's going to count this part as positive and this part as negative. And that's not what we want. We want the actual physical area. So the way to get around it is actually to put absolute values. So the area, now it doesn't matter which one is on top and which one is on the bottom. The absolute values will take care of making sure that you're always adding up positive areas. Unfortunately, it doesn't tell you how to compute this. You need to find the intersection point here. So when there's x equal to 1 over x, that's how you find out when two curves are equal, y equals x, y equals 1 over x. You just set them equal to each other. You get x squared equals 1. So x is plus or minus 1, and clearly we're not dealing with minus 1 because we're to the right of the y-axis. So that point, which was unmarked in the question, was 1. It's very possible that the point will not be marked, and you have to solve it, just like in this case. This is a particularly simple example of solving, at least, for x, the intersection point, but nevertheless, it is one that needs to be done. So anyway, we're going to write this as... There's two ways of doing it. I mean, you could just do it as the absolute value of each part, but maybe I'll do it a more elegant way. You see, from 1/2 to 1, 1 over x is bigger than x. So this absolute value is actually the negative of it. So in between 1/2 and 1, this quantity is positive. So this is the absolute value. Whereas between 1 and 2, x is bigger. And so that, you need x minus 1 over x. If you don't do that, if you put x minus 1 over x here as well instead of the other way around, you're fine as long as you take absolute values of each piece, just like we did over here. I mean, hell, you can even take absolute values anyway, but I guarantee they're both going to be positive in this case because I already put them the right way around. Top curve minus the bottom curve. You can choose your poison, do it any way you like. It doesn't matter. You're still going to have to do these integrals. Let's just do this one. The antiderivative of 1 over x is log absolute value of x. And an antiderivative of x squared, of x rather, is x squared over 2. I need to go between 1/2 and 1. And then, of course, you repeat for this one, and I leave that to you. Well, what do we get? We get log 1 minus 1/2 minus log 1/2 minus 1/4 over 2. And by the way, log of 1/2 is negative log 2. It's important that you know this. Log 1/2 is minus log 2. After all, it's log 1 minus log 2, and log 1 is just 0. So if you work this out, log 1 is 0. So this first piece turns out to be log 2 minus 3/8. Now I said I would leave the other piece as an exercise. It's actually spelt out in detail in 17.6.3. It turns out that you get 3/2 minus log 2. Not very difficult to do. So the true area is the sum of these two, which I can't quite fit on the board, but suffice it to say that it equals 9/8. If you work it out, the log 2's cancel out, and you get 3/2 plus 3/8. And that's kind of nice, except now we realize we wasted a whole bunch of time. Actually, what we should have done is taken this area here and just flipped it in this mirror image. And actually, we could have just found the area of this triangle all along. And that's a 3/2 by 3/2 right-angled triangle. So the area is 1/2 3/2 times 3/2, which is 9/8. So you didn't need calculus at all. But now, that's just being sneaky. Most of the time you don't get that sort of symmetry, but it's a nice reality check that the log 2's cancelled out and we end up with 9/8 after all. All right. That's all I wanted to say about fundamental theorems. That's chapter 17 of Calculus Lifesaver. There are a couple of extra chapters, like sections, proof of some technical point and the proof of first fundamental theorem, but that's the meat of it. So all that's left, as far as Math 103 is concerned, is the first of what's quite a large number of integration techniques. So in chapters 18 and 19 of my book, I do some different techniques of integration. The first one of which is substitution, and that has been put into Math 103. And of course, if you do continue with Math 104, you pick up with integration by parts and all the other methods, but we do have to cover substitution. So, any other questions about this fundamental theorem and basic sort of stuff? As I'm erasing the board, you have a little time to start vocalizing. All right. Okay, so I just intend to go over section 18.1. Okay, so we've already gotten some nice techniques about finding antiderivatives, but it turns out we can do a little bit better. By way of motivation, let's differentiate e to the x squared. To get integration, let's just differentiate e to the x squared. Well, according to the chain rule, I mean, the derivative of e to the x is just e to the x, so the derivative of e to the something is just e to the something. And in this case, the something's e to the x squared. The correction, though, that we have to do is multiply by the derivative of that something. And you get 2x e to the x squared. That's just the chain, nothing to it. Of course, we can convert this to an indefinite integral. Don't forget the plus c. It's an error to leave it out. You should be docked a point or two if you do that. So we have integral 2x e to the x squared dx is e to the x squared plus c. If you were just looking at it from this point of view, it kind of looks nasty, but it's really quite nice. You see, here, the x squared has sort of spat out its own derivative. Here it is, it's got to swallow it back up in. It's gone. We're undoing the operation. So you might think that actually this should be easier. The antiderivative of e to the x squared. But it's not. Blech. No one knows what that is. In fact, you can prove that you cannot find a nice expression for it, which is kind of unfortunate because it's related to those bell curves that come up all the time in probability theory. So You can use some series or some clever things to get some idea of what it is, but there's no nice expression for it. So actually, the 2x, although it looks like it's harder, it makes life easier. So anyway, what we're going to do in substitution, we're in the business of, is undoing the chain rule. Chain rule produces the derivative sitting out the front. We are going to use that and swallow it back up. So, here's how I propose to do it. Consider this an integral here. X squared cosine x cubed dx. It looks pretty nasty, but there's some hope. We're taking cosine of this nasty quantity, x cubed. I don't like taking cosine of x cubed. Cosine of x I can just about deal with, but x cubed, ugh. But luckily, the derivative of x cubed is sort of x squared. It's almost x squared. It's 3x squared. So we're going to use this. Here's how you can set this out. You can let t be this nasty quantity x cubed. If you did that, the integral, well, I don't know what to do about the x squared dx, but if I just consider this cosine x cubed term, that would just become cosine t, right? Because t is x cubed. And that's kind of nice. But I've got to deal with the x squared dx. Now, I could maybe write x equals the cube root of t, and sure enough, this would be t to the 2/3, but I'd still have the dx, and you cannot just change dx into dt. As x changes, t changes in a different way. How does it change? Let's differentiate this implicitly, as it were, or if you prefer, you could write dt dx equals 3x squared, but the useful form of this here is just to write dt equals 3x squared dx. I just put the dx, even though this is not a fraction, it's just the limit of a fraction. It turns out, and I do justify this in section 18.1.3, theoretical justification of this, I'm not going to do it now, it is just the chain rule. But it turns out that it is legitimate to replace dt by 3x squared dx. So you actually don't need to write it down, dt dx equals this. You can just write dt equals 3x squared and then write the dx. Now, actually, if you consider this piece together with this piece, that's almost 3x squared dx. It's actually x squared dx. So maybe we'll divide this by 3, and we'll write 1/3 dt is x squared dx. That is what I double underlined. So I propose over here to replace that double underline by 1/3 dt. Okay, I've used a squiggly line and a double underline to indicate what has been replaced. You do not have to put that when you write it out. I'm just doing this to illustrate what's going on here. You can, it doesn't really matter. It's not getting in the way, but I want you to understand that the x squared and the dx together have been wrapped into this 1/3 dt. Kind of nice. Now, what we have effectively done is moved from x land over to t land. We're now in the realm of t, not the beverage. The integral of cosine t dt is just sine t plus a constant. And we have this factor of 1/3 that just comes out the front since it's a constant itself. This is not the final answer because you cannot stay in t land. You have to go back to your roots in x land. And so we're going to replace t by x cubed again. Done. 1/3 sine x cubed plus c. As a reality check, we can differentiate this. You should use the chain rule. You'll get cosine x cubed times the derivative of x cubed, which is 3x squared. The 3 that comes out will cancel off with the 3, and you will get x squared cosine x cubed. So this example is almost simple enough to write down, but we'll look at some more complicated ones in a few seconds. Any questions about that for the moment? Now, by the way, some books use a u instead of t as a matter of course. And in fact, they even go so far as to call it a u substitution. This is not u substitution. This is substitution. You can pick any letter you like. I like t because when we do integration by parts in Math 104 or in section 18.2, we're going to use u's and v's. And there are a lot of problems that use integration by parts and substitution. And you can't reuse letters. So just don't call it a u substitution. Just call it a substitution. Let's be more mature about this and realize we can deal with any variable. But I do like t. All right, let's look at a couple more examples. Consider this one. Integral e to the 2x secant squared e to the 2x. Well, I don't really like secant squared of e to the 2x. It's kind of nasty. So let's let t be equal to e to the 2x. So dt, I need the derivative. The derivative of e to the 2x is 2 e to the 2x dx. So if I divide by 2, and the reason I do that is because I just have e to the 2x dx, not twice it. It's the same sort of trick. I get 1/2 dt is e to the 2x dx. So coming over to the integral, the e to the 2x dx becomes 1/2 dt, and the rest of it is secant squared of t, because t is e to the 2x. And as we saw earlier, the integral of secant squared is just tan, so this is 1/2 tan of t plus a constant. Are we done? No, we're still in t land. We have to replace t by e to the 2x. And again, you take this 1/2 tan e to the 2x plus c. Not a bad idea to differentiate it and make sure you get back the original. So if you do, you are going to differentiate e to the 2x, and you'll get 2 e to the 2x out the front, secant squared, and the 2's cancel out. Write it out if you need to, but convince yourself that you've gotten the correct antiderivative. There's almost no excuse, other than running out of time. There is no excuse for writing down an indefinite integral and getting it wrong. Really no excuse, because you can always check your answer by differentiating your answer and seeing if you get the original integrand. Okay, differentiating is much easier than integrating. I guess it's possible you could anti-differentiate wrong and differentiate wrong and do it exactly the same wrong thing so that your errors cancel out. But I mean, that's pretty unlikely. If you do run out of time, of course, then that's a different matter. But if you had enough time and you were going to leave the test early, just check all your antiderivatives. Just take a few minutes. You might find a mistake and get yourself some extra points. Right, let's look at one more example that leads to a general method. Here's a kind of nice example. Suppose you look at the integral 3x squared plus 7 over x cubed plus 7x minus 9. Ugh, looks nasty. It sort of does look nasty, but there's a minor miracle that occurs, and of course I've specifically concocted this example to have that miracle, and that is that if you look at the derivative of the bottom, x cubed plus 7x minus 9, the derivative is precisely what's on the top, 3x squared plus 7. So that suggests that if we set t is the denominator, x cubed plus 7x minus 9, that dt is 3x squared plus 7 dx, and that's exactly what's on the top. So this simply becomes, the whole top here becomes dt. And the bottom is just t. So this is dt over t, that's the same as 1 over t dt. So this is log of absolute value of t. And if you replace t by the denominator again, you just get log of the absolute value of the denominator. Okay, this happens so often that it's worth sort of writing it down as a sort of boxed formula. If you have an integral, which is a fraction, and such that you have a function on the bottom and the same function's derivative is on the top, exactly the same thing will work. If you just substitute t equals f of x, then dt is the derivative, f prime of x dx, and you will get 1 over t. In fact, I don't want to write it out. The argument is exactly the same as the top two things over there. You get dt over t, and you get log of absolute value of t plus c. So this is just the log of the absolute value of x, of f, plus a constant. And this is worth just knowing. It looks kind of formidable in symbols, but what it means is you can just write down the answer whenever the derivative of the bottom is on the top. It's just log of the bottom, absolute values. So here's a sort of straightforward example. Suppose I do the integral of x over x squared plus 8. What's the derivative of the bottom? X squared plus 8. What's the derivative? 2x. Well, we don't have 2x, but 2 is just a constant. So I'm not even going to bother with substitution. I'm just going to write down what I want it to be and fix it up by putting a half. You'll have to admit a half times 2 is 1. Why do I do this? Because now I can just write down the answer. I notice the derivative of the bottom is the top, so it's just log of the absolute value of the bottom. The only difficult thing is that I need that 1/2 there. Actually, I don't even need the absolute values since x squared plus 8 is always positive, but it doesn't hurt to have them. Here's another very brief example. How would you do 1 over x log x? Looks kind of nasty, but actually you can make your life very easy by writing this as 1 over x divided by log x. That's another way of writing that integral. What's the derivative of log x? 1 over x. So the derivative of the bottom is on the top, and you just get log of the bottom, absolute value. So it's log of absolute value log x plus a constant. Not too bad. All right. We've only got about 15 minutes left to finish substitution. So, anyone have any questions? I know it's rude of me to have my back to you while I ask if there's any questions, but what can I do? So much to do, so little time. All right. Okay. So, let's talk about definite integrals and substitution. Consider this example. Suppose I integrate from 0 to the cube root of pi over 2, a lovely number, of x squared cosine x cubed dx. Now this should look familiar. We did this indefinite integral before. In fact, if I resurrect what the answer was, I guess it's actually, maybe we can just pan all the way up to the top right corner of that board. There's where we did the indefinite integral. The answer was 1/3 sine x cubed plus a constant. So we could do what we did before, and I'm just going to put equals what we did before, or above, and you end up with an antiderivative. Forget about these bounds, just do what we did before, and we get an antiderivative of 1/3 sine x cubed. You don't need the plus c, so you go from 0 to the cube root of pi over 2. This is a completely legitimate way of doing it. You get 1/3 sine cube root of pi over 2 all cubed. That quantity minus 1/3 sine 0 cubed. And of course, cube root of pi over 2 all cubed is just pi over 2. Sine pi over 2 is 1. And you'll get 1/3 sine 0 is nothing, so this is just 1/3. That is method 1. To find a definite integral using substitution, first write down the indefinite integral, ignore the bounds, and work out that answer using this t substitution, or v, or u, or whatever substitution, whatever letter you want to call it. And then finally, once you found the antiderivative, just do what we were doing before. You plug in the two endpoints, the right minus the left. But there's a way of doing definite integrals without going back to x land. I'm sorry, yes, without going back to x land. We migrate to t land, and we stay in t land. Let me show you how it's done. We make the same substitution, we just have to do a little bit of extra work. But it's actually a little bit quicker in the end. How did we do the indefinite integral? What we did was we let t be equal to x cubed, because we were trying to take cosine of it, and it's nasty, so we'll let t be x cubed. We saw that dt was 3x squared dx, which inspired us to write 1/3 dt was equal to x squared dx. And what we started doing was we replaced bits and pieces of this integral. We changed the x squared dx into 1/3 dt, and we changed the cosine x cubed to cosine of t. But that's a definite integral, and you might be tempted to write 0 cube root of pi over 2, but that's wrong. So if you do this other method, you've got to turn it into an indefinite integral first. You have to get rid of the bounds as a separate column. See, this is wrong because these are values of x, not t. You also could do this. If you're going to try to keep it as a definite integral, you have to say, in words, when x equals 0, t equals 0 cubed, which is 0, okay? But when x equals the cube root of pi over 2, t equals the cube root of pi over 2 all cubed, which is pi over 2. So actually, I can erase these wrong things and write down the right things. 0 to pi over 2. So the moral of the story is, if you're moving a definite integral from x land to t land, or whatever variable you use, you've got to fix up not only the function itself, or part of it, you've got to fix up the dx into the dt, and you need to worry about the bounds. The x bounds have to become t bounds. And the beauty of this is you never have to go back to x land. You can just finish this as doing 1/3 sine t from 0 to pi over 2. And you get 1/3 sine pi over 2 minus 1/3 sine 0, and as before, sine pi over 2 is 1. Now, I agree, there's nothing different between these two things. It's just a question of writing it. But it normally is quicker to write it using the second method of changing the bounds as well. Okay? Any questions about that? All right. Not much more to say. Let's look at a couple more examples. Suppose I want to integrate this abomination. All right. 1 over inverse sine x square root 1 minus x squared dx. Well, let's let t equal inverse sine x, and the reason we do that is we've notice that the derivative of inverse sine x is very cunningly 1 over square root 1 minus x squared dx. So this expression, the dx over 1 over root 1 minus x squared is just dt. And this is 1 over t. Actually, this is just a special case of that log result that I wrote over there before. In any case, though, it's not legitimate to write 1 over root 2 or root 3 over 2 there. You have to be a little cleverer. You have to say when x equals 1 over root 2, t equals inverse sine 1 over root 2. What is inverse sine of 1 over root 2? What number has a sine equal to 1 over root 2? Pi over 4. You have to be good at trig and inverse trig. When x equals root 3 over 2, t is inverse sine root 3 over 2. What number has a sine of root 3 over 2? Pi over 3. So in t land, this integral actually goes from pi over 4 up to pi over 3. Completely different from the original bounds. And if you do this, you get log absolute value of t in between pi over 4 and pi over 3, which is log, everything's positive now, so log pi over 3 minus log pi over 4. And actually, it turns out that that's log 4 over 3. After all, you just divide this by this. Log of the difference is log of the quotient. And pi over 3 divided by pi over 4 works out to be 4/3. If it said simplify your answer, you'd have to put log 4/3, not log pi over 3 minus log pi over 4. There's no pi in the answer. All right, just a few more things. I want to talk about how to decide what to substitute. I've kind of been presenting it as fairly easy, but sometimes it's not that easy. Sometimes it's sort of obscure. So I'll spend a few minutes on that, and then I just have one more example, and I think that'll be it. So how do you decide what to substitute? We've been looking for pieces inside other functions mostly, but not always, whose derivatives are also lying around as a product. That's sort of the paradigm that you're looking for. So consider this example. E to the x, e to the 2x plus 1 dx. Well, there's a number of things you could substitute. You could try e to the 2x plus 1, but the derivative of e to the 2x has e to the 2x in it. That's not what we have up the top. So let's just try t equals e to the x. You get dt is e to the x dx. Well, there's the dt on the bottom, on the top. The whole top just becomes dt. What's e to the 2x? Well, e to the 2x is just e to the x all squared, which is t squared. So the bottom becomes t squared plus 1. That's a bit of a trick. So it's inverse tan t. It's an indefinite integral, so I better put it back to x land. All right, let's look at another example. I started 5 minutes late, so I'm going to finish 5 minutes late. Consider the integral of x times the 5th root of 3x plus 2. Well, a good rule of thumb is that if you see an nth root of a linear power, just let t be equal to that. Now, you could differentiate this to find dt, but you could actually play some nice tricks. You can do things like this. I'll show you the nice trick. Take the 5th power of both sides, and you get t to the 5 equals 3x plus 2. And then you can actually differentiate this implicitly both sides. The derivative of t to the 5 is 5t to the 4th dt. And the derivative of 3x plus 2 is 3 dx. That's actually allowed. So if you do this, let's just make x the subject. Let's solve for x here. And you get x equals t to the 5 minus 2 over 3. So all up, this integral is, this x is this quantity, t to the 5 minus 2 over 3. This is just t itself. And the dx is equal to 5/3 t to the 4th. I've divided by 3 in my head. dt. And if you work all this out, you can actually bust it up into two integrals. 5/3, you get 5/9. The first one will have t to the 5th, t, and t to the 4th, so you get t to the 10. And the other term is 2 times 5, 3 times 3, so you're going to get 10/9. But now the power is only t times t to the 4th, which is t to the 5th. And if you work this out, maybe I'll come up over here. I divide by 11, so I get 599 t to the 11. And now I divide by 6, so I get 10 over 6. I believe it's 5/27 t to the 6th. And then finally, instead of t, you have to put this 3x plus 2 to the 5th power. And you get this nasty mess. 3x plus 2 to the 11 over 5 minus 5/27 3x plus 2 to the 6 over 5 plus a constant. Again, you could differentiate this. It's not a bad idea to just check it by differentiating. And you should get the actual result. Okay, so I've only got one more thing to say, and I have 3 minutes in which to say it. So here it is. As a grand finale, I claim that if f is odd, then this is 0. We use this for the sine x from minus pi to pi. I'm just going to prove it. It's only going to take a couple of minutes. What the hey? Let's just start off with this integral. We'll split it up at 0. Let's just start from here. Minus a to 0. Let's make a substitution. T equals negative a negative x. So dt is negative dx. Also, we're going to change the bounds. When x equals minus a, t equals a, because t is negative x. And when x equals 0, t is 0. So according to the whole prescription, I'm going to change everything to t land. X is minus a, t becomes a. X is 0, t becomes 0. F of x is the same as f of minus t, because x is minus t, and dx is minus dt. So I've got a minus here. Of course, a minus allows us to switch the bounds on the integral. So I take this minus and magically flip them around. And I get the integral of f of minus t dt from 0 to a. A to 0, 0 to a. F is an odd function, so f of minus t is the same as minus f of t. And I bring the minus outside the integral. And finally, t is just a dummy variable, so after all this magic, I change it back to f of x dx. So, having gotten this formula, I now integrate from minus a to a. I'm just going to split up the integral at 0. So I get minus a to 0, f of x, plus 0 to a, f of x. And I just did all this manipulation. If you look at this, that's exactly what we just looked at over here. And we found that it equals this. So I'm just going to substitute that in. It's minus the integral from 0 to a, f of x dx, plus the same thing, integral from 0 to a, f of x dx equals 0. They cancel out. Okay? It's conceivable you could be asked to prove this in Math 103. Pretty unlikely, but who knows. In any case, you do have to be able to do all of the other ones, bread and butter sort of stuff. So, then, if you're watching online, until next time, which could be in a few seconds, you could continue with Chapter 18. If you're in the room, well, maybe you're doing Math 104, in which case I'll see you in February. So, that's all for now.